Hey everybody, it's Mr. N here, and we are going to do the fundamental theorem of calculus today. So as I've mentioned, there are two parts to calculus. For now, we have been focusing on this first branch, which is differentials. Okay, so we've talked about the differentials, and we've taken derivatives, and we've done the tangent problems. We've learned that the derivative is super important. The derivative is the slope of the tangent at a particular point. And we've learned that it's how to take the derivative. We learned power rule, we learned all the different ones. We learned the chain rule involved and everything else. But now we're going to shift gears and do the opposite. We're going to undo the derivative. So the second branch in calculus is the integral. And this is the antiderivative. So the integral here is the antiderivative. And this is how we've been doing, and we're going to do the area problems. So the fundamental theorem of calculus connects these two, and this is why I told you we were going to undo it. They are inverse operations, right? So you take the derivative, you undo it by taking the integral. You have the integral, you undo it by taking the derivative. They are inverse operations of each other. So here, this dates back to Leibniz and Newton, and they came up with this, and it started mathematical developments that fueled the scientific revolution. All right, so it connects fundamental theorem, and we often say FTC. That's what we'll say, fundamental theorem of calculus. So we'll just abbreviate it as FTC. So you'll hear me a lot saying, oh, we're going to use FTC. We're going to do FTC. And again, it connects integration and differentiation, enabling us to compute integrals using the antiderivative. So that's what I told you up above. The integral is the antiderivative of the integrand function, so we don't have to take Riemann sums anymore. Riemann sums, finding that area, well, that's the antiderivative. Whoa, 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 whoa. Mind blown. Okay, mind blown. So all those area problems, to find the exact area under the curve, all you have to do is take the antiderivative. That gives you the area under the curve. Amazing. We don't need to do all the rectangles and stuff anymore. So again, like I mentioned, Leibniz and Newton, they kind of came up with this and figured this out. And there's two parts to the fundamental theorem. Now, going back to Leibniz and Newton, Newton's often considered the father of calculus, but this couldn't have been done and couldn't have been presented because Leibniz organized it. Newton may have figured it out, but some say that Leibniz also figured it out at the same time, but Newton is given credit for it. But what Leibniz did is he gave us the notation, the proper way of saying things, the proper way of writing things. He organized it all in a manner that we can express, we can teach, and we can show others. So here's FTC Part 1. And again, a lot of books will flip-flop these parts. So they'll say Part 2 is Part 1 and Part 1 is Part 2. It doesn't matter. There's two parts to it. Know both parts. Part 1. If f is continuous on AB. So it needs to be continuous on a closed interval. The integral from a to b of f of x dx equals capital F of x from a to b, f of a minus capital, f of b minus capital F of a. So f of x is the antiderivative. So in other words, if I take the integral, I will get the original function, which is the antiderivative. So I can also say that the derivative of the original is little f. So what does this do? This allows us to solve a definite integral by plugging in the bounds. This results in the area under the curve without having to do Riemann sums. So what this is telling me I can do is I can take the integral over these bounds, plug it in, and I get the area. And I don't need to do Riemann sums. So part 1 tells me don't do Riemann sums anymore. Take the integral, that gives you the area. All right, let's look at part 2. Part 2 says, if f is continuous on an interval I, then f has an antiderivative on I. In particular, if a is any point in I, then the function f is defined by capital F of x equals a to x f of t dt. it is an antiderivative of f on I. That is f prime of x equals f of x for each x in I. So we can note this as the derivative with respect to x of the integral is the original, because the derivative and the integral undo each other. So part 2 just tells me that the derivative and the integral undo each other. So the derivative of the original, capital F of x, will give me the little f of x. Now, capital F of x, if the little f of x was the curve, capital F of x will be the area. That's for the part 1. And part 2, the derivative of the integral is just going to leave me with what I have right there. Okay? So this just basically tells us how to find the derivative of the original. So there's 2 parts to FTC. Now, if you YouTube FTC, remember, whenever I say fundamental, that's going to be something that's super important. Whenever we say that in math, fundamental, ooh, that's big. Fundamental theorem of algebra, fundamental theorem of calculus. Well, if you YouTube it, you're going to get a lot of different explanations. You're going to get some crazy videos, people doing songs and dances for it. But the bottom line is, however you need to remember it that way. And for one part, it's just if you integrate, you're going to get the area under the curve. For the second part, if you take the derivative of the integral, you're going to get whatever you started off with as far as being this function right here, which is the curve. So the derivative of the integral undo each other. Those are the 2 parts. Area on the curve, derivative of the integral undoes itself. All right, so let's continue on with some things here, because now, all right, so notice when I did this in part 2, I had a t. So I had said that capital F of x right here equals the integral from a to x of f of t dt. Okay? And then when I took the derivative with respect to x of this from a to x of f of t dt, right here, dt, this gave me the f of x. So these 2 undid each other, but then the x went in right there. All right, so you can think of the dx as the rate, the slope at x, and the f of x as the instantaneous rate change of x. So notice that a is the lower bound and has nothing to do with this final answer. So when I took the derivative with respect to x of this integral, the a went away, but the x got plugged in, right? And that just comes from the fact of the integration for part 1. So basically, as already noted in the derivative, the integral are inverse operations. The derivative and the integral are inverse operations of each other. So here's where we need to be careful because of this a. So here's our first FTC example. Find the derivative with respect to x of the integral from 2 to x of 1 minus t cubed dt. So look at the constant term. This is 2. So over here, what ends up happening is the derivative and the integral undo each other. I plug this x in, and I will get 1 minus x cubed as my answer. Well, again, taking a look at what I had just said, what happens to this 2? What happens to this 2? It goes away. Now, often we will call this the dummy variable because it just goes away. So I can change this dummy variable to be whatever I want. Again, I didn't give it this term. This is what a lot of books call it, the dummy variable. These go away. That doesn't have anything to do with it in the problem, and I still just plug this in. So this answer would be the same exact thing as above. So this has nothing to do with the problem because it's like taking the derivative of a constant term. So notice that the answer doesn't change that constant term, which is the lower bound, which is the dummy variable. All right, let's move this up. But what if I change the upper variable, the upper limit? What if I change that? What if I made that x squared? Okay, so now let me do this problem for you, and you can see what I did over here. So let's choose a different pen color to make it stand out a little bit. All right, so these are going to go away. I'm going to plug this in here. Right? The 2 doesn't matter because it's the derivative of a constant. It goes away. But I'll end up with 1 minus x squared cubed times 2x. There's my answer for this one. So let me put this in parentheses, right? And I can clean this up if I wanted to. and just write this as 1 minus x to the 6th times 2x. Yes, I can distribute, but I'm just going to clean it up like this. Wait, what happened here? What did I do? Look at, I took the derivative of this as well. Why? Because of the chain rule. So we have to still keep into account the chain rule. I did take the derivative here, times 1. I did do that. That's the chain rule portion of it. So you still have to apply the chain rule because it's a derivative. Anytime we have derivatives, we got to use the chain rule. So some books will do this with a substitution type method. I think this chain rule method that I just showed you is a little bit easier. So now let's take a look at this next one. What if we've got a couple more things going on here? We've got the limit from, wait a minute, wait just a cotton picking minute. I don't know why I said that, but there you go. I guess I'm old now. Okay, anyway. All right, so here's x, and it's down below. It's the lower limit. What the heck? Look, this fix is easy. All you got to do is put it back up top right here as an upper limit and do that. Because remember I told you, if you have the integral from a to b, this is the same as saying that negative the integral from b to a. You can flip the bounds whenever you want. You just have to change it to be a negative. So that's all we got to do there. And then we continue on the problem. We have negative d dx from the integral from 2 to x, 1 minus t cubed. And now it becomes pretty much the same. I'm going to go ahead and plug this in, but I'll have the negative. Those undo each other. There's chain rule is just 1. So 1 minus x cubed with that negative out in front this time. Okay, now one more. What if both upper and lower limits were variables? What do I do now? Okay, so take a look. And here I'm going to just break this apart with the integration rules I learned. The derivative with respect to x of x to x squared of 1 minus t cubed. Look, I'm going to just say x to a. Then I'm going to say a to the x squared. So this is, I just picked some arbitrary point in between. I'm going to take the integral to that arbitrary point, then from that arbitrary point to the other one. And guess what? I'm going to do this. I don't want the x down below. I need the x up top because down below is going to be that dummy variable. So then I just flip it and put a negative. So this becomes negative d dx from a to x. And then I can plug these in. I can go ahead and solve this. So these go away. This will be negative, and we've already done this problem. This is 1 minus x cubed, right? And then plus, these go away. I plug this in. That's the dummy variable. I take the derivative of a constant, and it goes away. So this becomes 1 minus x squared to the third times my, I need to chain rule it, 2x. So there you go. That's how we do those. All right, so here we've got a few more examples that we're going to do, and I'm going to show you in a little bit how to do them on your calculator. So for this first one, we need to evaluate and verify, and then with our calculators, I'll show you. But this is the integral from negative 1 to 4 of 6x dx. Okay, so FTC told us that the integral is the antiderivative. So I need to take the antiderivative here. That's what the integral tells me. And what does this mean? This means I'm finding the area under the curve of f of x, 6x, from negative 1 to 4. So the antiderivative here becomes x squared, 3x squared. And then from FTC, I'm going to be plugging in these bounds. So I put the bar like this. Sometimes you'll see some books drawing that bar like that, and they'll say negative 1 to 4. Either way is fine. So from negative 1 to 4, that means I'm going to plug the 4 in. So I'll have 3 times 4 squared, and then this is minus 3 times negative 1 squared. You could have also set this up as 3 times 4 squared minus negative 1 squared. Okay, either way, because they both have that 3 in common. The constant is a 3. I could have taken that out when I evaluate it on those bounds. Okay, so this ends up being, if I do this one, either way you could do it. It's going to be fine. So 16 times 3, 48, minus, this is going to be 3. Your answer is 45. Okay, for the next one, I'll show you the calculator in a minute. Let me do a few of these, and then I'll show you that. All right, over here. This is a constant. I need to take the antiderivative, so that's just going to give me 5x on the bounds from 3 to 4. So this means 5 times 4 minus 5 times 3, 20 minus 15, and this will give me 5. Over here, this is x to the 1/2 on these bounds. So when I take the antiderivative, I'm going to get 2/3 x to the 3/2, right? 3/2, 2/3, that'll work it out on the bounds from 1 to 4. So then over here, I'll get 2/3 times 4 to the 3/2 minus 2/3 times 1 to the 3/2. And then cleaning this up, I will get 14/3 as my answer. So let's take a look at this next one. The integral from pi to 2 pi of sine theta d theta. Okay, so I take the antiderivative here. This is negative cosine theta on the bounds from pi to 2 pi, which gives me negative cosine 2 pi minus negative cosine pi. This becomes negative 1 plus negative 1, which is negative 2. Moving right along, we've got this one over here, and we have the integral from negative 1 to 4 of 1 over x squared. So we will go like this, x to the negative 2 dx, right? Take the antiderivative there. That's going to be x to the negative 1. So this will be negative 1, x to the negative 1 on the bounds from negative 1 to 4. All right, so I put that in. So that's going to work out to be negative 1, and I'm going to do it this way this time, 1/4 minus 1 over 1, negative 1 over 1, sorry about that. So this will give me, this will be plus 1, so 1 and 1/4 in here, and then the negative, so negative 1 and 1/4 as my answer. That's wrong. All that is wrong. The answer to this is no solution. What the heck, Mr. N? Why did you do that? Why did you make me do this whole problem and then you tell me it's no solution? Because there's one important thing you got to pay attention to. Look at these bounds right here. Check this out. Here's my closed interval. From negative 1 to 4 is my closed interval. And the theorem for something in FTC to be integrable, it needed to be continuous in this closed interval. Guess what? At 0, it's not continuous. There's a discontinuity at x equals 0, and so because of that, there can be no solution. So just think of it. If it's going down discontinuity in this case, if you graph this, you will get this particular function that looks like this. Now look, at 0 right here, it goes, there's an asymptote, it goes up to infinity. How can I know how high the rectangle is? How can I find the area? I can't, so there's no solution because the rectangle at that point is infinitely tall, so there is no solution to it. So one thing to always note, you better check the bounds. You got to make sure that it's continuous on the bounds they give you. So you need to always check that. So let me do these next two, and I'll show you something on your calculator for how you can do these. Over here, this next one, yes, it's going to be continuous on the bounds because it's a polynomial. So for this, I will get 1/3 x cubed plus x squared plus x when I integrate it from negative 3 to 4, which will give me 1/3. This is x cubed, I should have said. I said it, but I didn't write it. And this will give me 1/3 times 4 cubed plus 4 squared plus 4, this, minus 1/3 times 3 squared, that's this whole thing minus, plus 3 cubed, 3 cubed plus 3 squared plus 3. It looks like that. So all said and done, you get 44 1/3. Next problem, I take a look at this. Wait a minute. I can't put negative 2 in there because it won't be continuous, so no solution. Because it's not continuous on the closed interval of the bounds. All right, so here's how we do this on our calculators. So take your calculators out. Let's take a look at it. And you're going to do the same thing that you did for the derivative. You're going to use that FNINT feature instead of the n derivative feature. So here's what your calculator is going to look like. And you are going to hit the following. You're going to hit the math button and then choose the one option that says FNINT. And that's the integral function. And you'll get this. So you'll just put the whole integral in. The lower bound, the upper bound, put in the equation with respect to x. Don't worry about this bottom part. And then hit enter, and you'll get a value. So try it for each of these, and you should get the values that will work out. Now, if you have the old software, you're going to have to do it like we talked about before, FNINT, then it's going to open the parentheses, right? And you'll have to put the equation, then the upper bound, then the lower bound, then x, and close it out. And then hit enter, and it should give you the answer. So that's for the old software. But the new software, you will just get the integral that looks like that. There are many more examples of FTC that I want to show you guys, but I'm going to put those in different videos with those examples because this lesson is long enough and this one just basically covers the basics of it. So look for the other videos coming where I'm going to be specific with certain types of problems and things that you'll see on the AP test. So thanks for watching. Hit that like and subscribe button, and I'll see you guys in the next video.